All right, thanks. Yes, thanks, Sam. All right, my apologies for this technical issue. So, hello everyone. I'm Ye Zhao. I'm an assistant professor in mechanical engineering, and today I'm going to talk about some of our more recent works, especially on how electric robots can safely navigate and coordinate, especially in challenging, dynamically changing and challenging environments. So just as a very high-level overview, I direct the Laboratory for Intelligent Decision and Autonomous Robots, the LiDAR group at Georgia Tech. My group has a large focus on task and motion planning, decision-making, and control algorithms for highly agile robotic systems, especially like locomotion and manipulation. And our group is particularly interested in computationally efficient trajectory optimization, formal method for challenging robotics problems, especially those involving contact behaviors, and how to reason about or even provide formal guarantees such as safety, robustness, and collaborative behaviors. So this recently received NSF career project is about robust, scalable task and motion planning, named as Interactive Decision-Making and the Resilient Planning Framework for Safe Robot Locomotion in complex and human-populated environments. And specifically, we aim to design risk-sensitive trajectory optimization that can handle contact uncertainties and generalize this trajectory optimization to versatile contact behaviors by the adversarial regularization-based policy learning approach. And then we are going to integrate this robust trajectory optimization into a hierarchical task and motion planning framework with multi-level locomotion safety. And we are especially interested in like the navigation in partially observable environments, incorporating not only reactive interaction with dynamic obstacles, but also proactive interactions with humans and predict human intentions. And this project actually just started this month, so unfortunately I don't have a lot of results to show. So in this talk, I'm going to present some preliminary results and some other works very related to this, basically serve the backbone of this project. So our group, over the past few years, have been focused a lot on this temporal logic-based or formal method-based like navigation. So we have been exploring this from multiple different perspectives, including whole body locomotion planning through these constrained environments, and safe learning planning, being aware of environmental uncertainties, as well as heterogeneous robot teaming with this task reallocation and failure recovery capabilities. And along this direction, we have a large focus on scalable, safe mission and task planning, especially for long horizon robotic tasks. So for example, here you can see how we can make the KUKA robots manipulate, sort the object into the box, and then the CAS robot is going to pick up the box and deliver the box to a destination downstairs. And some key research questions we are interested in includes like how the manipulators are going to manipulate these very complex objects, how the walking robots can avoid collisions with other dynamical obstacles in the environment. So we basically study contact-rich and collision-free robot behaviors simultaneously. And as a very recent collaboration with Sam Coogan's group, most basically the PhD student Jesse Jiang, we propose an abstraction-based formal method named as interval Markov decision precise to synthesize control policies for this robot to safely navigate the environments. And we also incorporate a stacked GP learning approach to handle multiple sources of environmental uncertainties, including terrain uncertainties, and how to guarantee the safety even without violating the LTL specifications. So here, a very central research question we are interested in is how to guarantee like the robots can safely navigate in partially known environments at the same time accomplish a very complicated teaming task as those seen in the autonomous mobile robots in warehouse. So there are several key considerations. So first, the like robots need to think about how to balance first. So balancing safety, like where it should put photo locations, and at the same time, navigation safeties, how to avoid collisions with other obstacles or humans, etc. And another key component is the environment, which often involve rough terrain, partially observable features, environmental uncertainties, and also the robots only have a local field of view of the environment. So in this case, how we can parameterize and abstract the environments? Are we going to use fine or coarse abstractions? So all of this is going to give us different computational workload and different planning capabilities. And the last but not the least is the robot always want to collaborate with other robots, humans, for cooperative tasks. So to enable safe locomotion in this partially observable environments at the low level, we design safe locomotion gates using our phase-based motion planner, which basically plans the foot locations and the center of mass apex velocities. And based on this reduced order walking model, we propose a series of locomotion safety criteria. So I will not go through the mathematical details, but conceptually speaking, you can think this safety criterion basically tell us how much robot's apex velocity can change between two consecutive walking steps and how much turning angle there is allowed given specific walking speed. And then we encode this safety criterions into the high-level task specifications. And this is a big distinction from a lot of other people's work. When they study navigation problems for lagged system, they literally just treat their walking robot as a point mass or maybe a standard mobile robot and ignore a lot of physics constraints from the lag dynamics. So basically, by encoding this safety criterion into the high-level task planning, we can make sure the task-level decisions can be successfully implemented and executed by the underlying motion planners and the controllers. So overall, we have this hierarchical planning structure composed of a task and the motion planner layers. At the high level, the task planner aims to solve, to guarantee these navigation specifications, including safety specifications like avoiding collisions and visits specific locations infinitely often, and other specifications as well. And then this high-level task planner is going to send discrete locomotion commands to the middle-level motion planner for this 3D locomotion plans, which have the capability of maneuvering rough terrain and steering directions in the complex environment. And then we send it to the underlying full-body trajectory optimization for the entire leg motions. And this framework is implemented in this two-stage open environment with dynamic obstacles. So we frame this navigation problem as a two-player game between the robots and the adversary environment. So in this case, the grounded mobile robot is treated as the uncontrollable environmental events. And the walking robot Cassie also have a belief abstraction of the environment shown in this colored region, and basically infer the potential dynamic obstacle locations when these dynamic obstacles are out of the local set of view, so it can infer the potential obstacle locations. But there's a big limitation for this temporal logic-based reactive synthesis in the fields these days, and many times this approach enforces strong assumptions about the allowable environmental events, which is sometimes not consistent with the real physical world. So really to address this problem, we propose a heterogeneous robot teaming of bipedal and aerial robots working together. I'm not sure why. Oh, the video is playing. Okay. To address this environmental conflict online that is actually not addressable by the standard offline synthesis approach. And for example, in this case, you can think there's a drone system trying to fly through this area, but there's a door kind of block the drone's system pass that is only detectable at runtime. And then it's going to send a signal, ask for assistance of the digital walking robot. And then the digital walking robot is going to stop its current task and come to help the drone open the door. And then the drone can fly through, and then this robot can finish their remaining task. And so in this case, we propose a new online replanning framework to detect such a failure case and the resynthesis of the robot's motion behaviors to help resolve this conflict. So moving forward, these days we are looking at navigation problems in human crowded environments. So how we can infer human navigation intentions through proactive interactions with humans and predict the human navigation paths through the state-of-the-art neural network approach. And more importantly, we want to incorporate this human predictor module into our MPC-based robot motion planner through this risk-sensitive approach by conditional value at risk. At the same time, we also look a lot at this multi-contact locomotion and manipulation problems, so how to solve optimal task allocation and planning, especially for the object-centric contact planning. So we are very interested in signal temporal logic approach to specify collaborative locomotion and manipulation task specifications for complex interactions with the environment and objects, and then how to transform this into mixed-integer program for multi-contact modeling, and which many times inspired by this virtual linkage model inspired from the grasping community. And this problem is framed as a reactive synthesis through this min-max optimization, where the contact uncertainty is treated as a disturbance, which try to falsify the robot specifications. So this is a new project we are looking at these days. So it's about the contact sensing-rich bipedal robot avatar with a soft super limb arm. And this is definitely a joint work with multiple groups, Thess Hutchinson, Yue Chen, and a few others. And so also equipped with this gel set tactile sensing as the fingertip and this morphologically reconfigurable robotic foot, these new humanoid robot digits basically have high resolution contact sensing capabilities for both locomotion and manipulation. And we are still exploring the right way to approach this contact-rich sensing information and how to integrate it for planning and decision making. So I think I don't have a lot of time, but I just want to quickly highlight this very recent work on trajectory optimization, which is another big focus of our lab. So we study this angular momentum aware trajectory optimization and MPC. We propose a alternating framework to achieve dynamic consensus of centroidal momentum-based optimization and the whole body optimization together. So basically, by explicitly parameterizing the ellipsoidal moment of inertia of the robots and getting more feedback from the whole body dynamics, we can achieve a series of dynamic motions on this mini cheetah robot, and also including this 180-degree spinning. So we compare some the performance with some traditional approach in the literature. At the very, very end, I just want to highlight this another approach on task motion planning for push recovery that are resilient to many different kind of perturbations, any direction, perturbations at any magnitude can be applied at any locomotion phases. We have extensive evaluations of this framework in the current system in human augmentation space in high bay. So we basically evaluate study the recovery strategies in terms of multiple different perturbations. And we'll also think about how to leverage human inspired locomotion strategies for this robot recovery strategy, and also leverage for exoskeletons for assisting and augmenting human recovery capabilities. And at the very end, as a concluding remark, I think although there are still a lot of challenging problems for humanoid robots like sensing, autonomy, behavior reasoning, but I think there's no doubt nowadays we are really transforming these humanoid robots from science fiction to reality. I may be biased, but we are already in 2022, so let's see what's going to happen for the AI Day next month, and let's see what Elon Musk can bring to us. Hopefully, he can really show some really impressive results on this optimum project and don't make us feel disappointed. So with that, I'm going to stop. I hope I didn't take too much time. Thank you.